numbers, strings, and money in banking. In this lesson, we will learn how to use Python to work with numbers and strings to analyze money data from real banking transactions. This problem matters because banks handle huge amounts of numeric data, transaction descriptions, and strings every day. By the end, you will understand how to process, clean, and analyze numbers and amounts, work with money safely, and avoid common errors. You will build skills to extract value from messy text, convert values correctly, handle rounding, and automate checks for financial data. Running the cell now. Before we start solving problems, we need to set up tools for working with tables, arrays, and warnings. We import pandas to handle tables and data frames. We import numpy to generate random numbers and work with arrays. We import the warnings module to filter less important messages. We ignore warnings so that output is cleaner and easier to follow. Running the cell now. Try these imports on your own notebook. Next, we will see how banking transaction data is structured. Core data concepts, banking transactions and money. Banking transactions contain numbers, amounts, strings, reference info, and dates. Amounts must be handled carefully to avoid losing cents due to rounding. Transaction descriptions are messy strings and may contain errors or noise. Beginners often forget to use the right data types for amounts and dates. We must always work with the right formats to keep money calculations safe and precise. Running the cell now. Let us generate a realistic dataset of banking transactions using Python. This will help us understand how numbers and strings appear in banking data. Set the seed for reproducibility so that our random numbers are the same every time. We set the number of transactions to 1000. We set the number of unique customers to 200. We create a new data frame to store the records. We create transaction identifiers from 1 to number of transactions. We randomly assign a customer to each transaction. We generate realistic numeric transaction amounts using a normal distribution. We randomly assign a transaction type, such as debit or credit. We assign a transaction channel, like ATM or online. We create dates on an hourly basis from January 2024. The data frame is now built and ready for us to analyze. We print the shape to confirm rows and columns are correct. We print the first 3 rows to see what our data looks like. Running the cell now. This output shows a data frame with 1000 banking transactions and 6 columns, including carefully rounded amounts to 2 decimals, ensuring cents are preserved. Notice the mix of data types, strings for customer IDs and transaction types, floats for amounts, and date-time objects for transaction timestamps. This alignment is crucial for accurate financial data handling. The snippet also demonstrates generating realistic, messy banking data with multiple customers, channels, and transaction types to practice core data concepts. Try to change the number of transactions and rerun this cell. What happens to the shape and sample output? Amount is the core metric in banking transactions. Let us check its data type and a few sample values. Print the data type of the amount column. We want it to be float. Show the first 5 numeric amounts from our synthetic banking transactions. Running the cell now. The output confirms that the amount column is stored as a float 64 type, which is appropriate for keeping cents without rounding errors. The first 5 amounts show precise decimal values, highlighting the importance of using a floating point type to accurately represent transaction amounts in banking data. This step ensures we handle money values correctly before any further processing. Why is it important for the amount to be a float, not a string or int? Try converting it and see what happens. Bank statement columns usually include both numbers and strings. Strings like transaction_type or channel help describe the transaction. Print the unique values found in the transaction_type column. This shows us which types of movements happen. Print the unique values for each transaction channel. This helps in channel analysis. Running the cell now. This output shows the unique categories in the transaction underscore type and the channel columns, confirming that transactions are classified as either credit or debit, and that they occur across multiple channels like ATM, POS, online, and branch. Noticing these unique values helps us verify that the data types and contents align with real banking operations, which is crucial for accurate categorization and analysis later. Strings often need to be standardized. Try adding a new transaction type and rerun to see if Pandas shows it. Amounts should often be presented as strings with a $sign for reporting or for clients. We round and convert numeric amounts into strings that look like real money, keeping 2 decimal places. We apply a formatting function that inserts commas for thousands and shows cents for every value. Print the original amount and the formatted string side by side for the first 3 transactions. Running the cell now. Here we convert numeric amounts into formatted strings that always show 2 decimal places, preserving cents accurately. Notice how the original amounts, like 238.77, are precisely formatted as currency strings, like $238.77, which is crucial for clear financial reporting and avoiding rounding mistakes. This step ensures amounts remain human readable while maintaining exact values. Try changing the currency symbol or the formatting string. Can you make it show euros instead of dollars? Sometimes, string representations of amounts need to be turned back into numbers for calculations. Remove the $sign and commas before converting the string back to a float. Apply the conversion to the first 3 formatted string amounts. Print out the reconverted values to verify correctness. Running the cell now. This output shows the first 3 amounts successfully converted from formatted strings back to floats, preserving the exact cent values without rounding errors. Notice how the code carefully strips $signs and commas before conversion, which aligns with the lesson's emphasis on handling monetary data accurately to avoid losing precision. This step is crucial because using the correct numeric type enables reliable calculations on banking transactions. Be careful stripping characters when converting money strings. One mistake can make numbers totally wrong. Let us do a basic sum over all numeric amounts. This is a common first step in banking analysis. Sum all the amounts in the data frame using the sum method. Store the result in the total_sum variable for future reference. Print the total value, nicely formatted as money. Running the cell now. This output shows the total sum of all transaction amounts in the dataset, formatted to 2 decimal places to preserve cents accurately. Notice how using the correct numeric data type ensures the financial total is precise and rounded properly, which is critical when dealing with money. This example highlights the importance of handling amounts carefully to avoid errors in financial calculations. Try replacing sum with mean. What does that value show you about the transactions? Understanding the count of credit versus debit transactions is a basic need for both banks and clients. Use value_counts to see how many credits and debits exist in our synthetic data. Store the counts and print them out for analysis. Running the cell now. This output shows the count of credit versus debit transactions in the dataset, with 503 credits and 497 debits, indicating a nearly balanced mix. Notice how using value_counts quickly summarizes categorical transaction types, which is essential for understanding the data distribution before deeper analysis. This step reinforces the importance of correctly categorizing transaction types as strings to capture meaningful distinctions in banking data. How might the ratio between credits and debits change for a savings account versus a credit card? Banks should never see negative amounts on deposits. Let us detect any bad values and correct them. Extract any transactions where the amount is less than 0. If any such rows exist, notify how many were found. For each, print out a message before fixing. Set those bad amounts to 0 for data safety. If no negative values are present, report no action needed. Status update for clean data. Running the cell now. This output shows that the code detected 7 transactions with negative amounts, which are not allowed in this context. The key action here is replacing these negative values with 0 to ensure all amounts are valid and consistent for further processing. This highlights the importance of data validation and cleaning when working with financial amounts in transaction data. What other simple checks could you run to clean up the amounts column? Transaction descriptions are messy and often contain numbers buried in text. Let us try extracting them using regular expressions. We define a list of example transaction descriptions with embedded amounts. Import the re module to help us perform pattern matching on strings. Use a regex pattern to find the value after a $sign, then convert to float safely. Print out the extracted amounts for each example phrase. Running the cell now. This output shows the extracted numeric amounts from messy text descriptions, demonstrating how regular expressions can isolate dollar values within strings. Notice the amounts retain their decimal precision, which is crucial for handling money accurately. This step is key to converting text data into proper numerical values for further analysis or calculations. Try changing the text to see how flexible your pattern is. What if the $sign is missing? Rounding is crucial in banking. Let us see how to round off all our amounts to the nearest whole dollar. We create a new column that contains the rounded transaction amounts. Use the round method, specifying 0 decimals, for bank-style rounding. Display first few entries to see the original and the rounded values. Running the cell now. Here we see the original transaction amounts alongside their rounded values, demonstrating how amounts are rounded to the nearest dollar using bank rounding. Notice the subtle differences where cents are either rounded up or down, which is important to preserve accuracy when simplifying data for reporting or analysis. This step highlights the careful handling of numeric types to avoid losing precision in financial data. If you work on financial reporting, always clarify with your team which rounding rules to use. Reports usually compress all details into a single human-readable string for quick review. Take the first row as an example transaction. Build a summary string with the date, type, channel, and amount nicely formatted. Print an example output summary for validation. Running the cell now. This output shows a clean, readable summary of a single banking transaction, combining the date, type, channel, and formatted amount into one string. Notice how the date is correctly formatted as YYYYMMDD, and the amount retains its cents with a $sign, demonstrating careful handling of data types and string formatting. This step is key for creating user-friendly reports from raw transaction records. How would you change the format if you need to include the customer ID as well? Customers want to know how their balance changes with each transaction. Let us create a running total for one customer. Filter the data frame to only one random customer and sort by date. Compute the cumulative sum of all their amounts to get a running balance. Print out the first 5 balance values to check the series. Running the cell now. This output shows the running total of transaction amounts for one customer, sorted by date, illustrating how their balance changes with each transaction. Notice the cumulative sums are precise decimals, preserving cents without rounding errors, key for handling monetary data. This confirms that filtering and sorting by date before calculating balances helps track financial activity accurately over time. Try plotting this balance over time using Matplotlib or Seaborn to visualize the account history. Banks often flag or block unusually large transactions for review. Let us add a flag for high-value cases. Set a threshold value that is considered large enough to flag. Create a Boolean column that marks true when the amount exceeds this threshold. Display the first few rows showing which transactions are flagged for review. Running the cell now. This output shows the first 5 transactions with their amounts and a new to flagged column indicating whether each amount exceeds the high threshold of 500. Notice that all flagged values are false here, meaning none of these sample amounts are suspiciously large. This step highlights how to identify and mark significant transactions without altering the original data, reinforcing the importance of careful numerical comparisons in transaction processing. Experiment with different thresholds, for example, flag all credits above $2,000. Unstructured transaction logs often pack everything into one messy string. Parse and split them into usable data. Create a sample list of messy transaction logs as a pandas series. Split each string by the colon separator into individual pieces. Label the resulting columns for clarity. Extract numeric amounts from the string, removing the $sign. Show the new, clean data frame for comparison. Running the cell now. This output shows how a messy string of transaction data is split into clear, structured columns for date, channel, and amount. Notice the amount column is correctly converted to floats, preserving sense and ensuring accurate numeric handling, an important step for reliable financial calculations. This demonstrates the importance of using proper data types and string parsing to clean messy transaction records. Try to add a new pattern with missing channel and see how your code behaves. Sometimes strings cannot be converted to numbers. Here, we handle the error gracefully. Use a try-except block to catch conversion errors. Try to convert a badly formatted string into a float. If there is a value error, catch it. Print the error message for learning. Running the cell now. This output shows an error message when trying to convert a non-numeric string, $100, to a float. It highlights the importance of proper data cleaning and validation before processing amounts, as transaction descriptions often contain messy text that cannot be directly converted to numbers. Handling such errors prevents crashes and ensures accurate financial calculations. Always handle possible conversion errors, especially with client-supplied or legacy data. Often you must clean extra words and white space before you can do math on money columns. Define a sample amount string with extra text and spaces. Try to remove the currency label and trim white space. Convert to float if possible. Print out the final value for confirmation. Catch exceptions if conversion fails. Otherwise, print an error message. Running the cell now. This output shows the cleaned and converted amount from a messy transaction string, successfully stripping currency labels and spaces before turning it into a float. Notice that careful text cleaning is essential to avoid errors and accurately handle amounts, which is critical for precise financial calculations without losing sense. This aligns with the lesson's focus on using the right data types and pre-processing steps for transaction amounts. Write your own version that also strips commas and parentheses. Best practices and lessons learned. Always use float or decimal types for money, never plain strings. Convert and format amounts early, check for negative and huge values. Clean and validate input before doing math, expect inconsistent formats. Strings can hide valuable info. Use regular expressions wisely. Use try-except for all type conversions involving user data. Running the cell now. Let us walk through an entire example, parsing text records, extracting amounts, and calculating account balance. Define a list of raw transaction strings, each with a date, type, and formatted amount. Split each record by the colon to break into columns. Convert the list into a data frame for processing. Remove a USD from amounts and convert to float numbers. Sum all the numeric amounts to get the account balance. Print the final account balance, demonstrating the full workflow from raw input. Running the cell now. This output shows the total account balance calculated from raw transaction strings, highlighting the importance of extracting and converting string amounts into floats early for accurate math operations. Notice how the code splits, cleans, and converts the amounts before summing, demonstrating best practices for handling money data to avoid errors or misleading results. Try adding a new transaction. Does the summary and balance update as expected? Subscribe to our YouTube channel for more tutorials and real banking data projects. Recap: you mastered numbers, strings, and safe money processing. You learned to convert, clean, parse, and format amounts. You learned how Python can avoid expensive banking mistakes. Keep exploring, try new string patterns and error tests. Watch more practical banking tutorials on YouTube. Running the cell now.